Bismillahirrahmanirrahim. So today I want to talk to you about multivariate random variables. Basically, the 6 lectures that you are supposed to have studied deal with one random variable. Yesterday, in last lecture, I explained what a random variable is and what a distribution is. Now I want to consider what are two random variables. Now, one thing that I want to explain to you is that this exposition that I am going to give you is not available in any textbook. It is an understanding that I have developed after thinking about these problems for a long time. If you look at any textbook of probability and statistics, you will find a definition of random variables, but it will be very different from what I am going to tell you. And what I am going to tell you will not be found anywhere. So the first thing to understand is that random variables and distributions, these are mental models. They exist only in our minds. They don't exist in reality. So what is the point of a mental model? Why should we think about theories which don't have any application, which don't have any counterparts in reality? For example, suppose that I say here is a binomial random variable, it has this property, that property, and we can study all of the properties that these are independent, and probability of heads is 1/2 and probability of tails is 1/2. But this is all a theoretical thing. Now when I actually take a coin and I flip it, then is this a random variable or not? This is the question about which there is a lot of discussion. Now what I would like to tell you is that there is a statement you can find in places that all models are false, but some models are useful. So this is one way to think about it, that we have this model. It is false, but it might still be useful. And this is actually much better understanding. So let me say, level 0 understanding is to ask, is the flip a random variable or not? This is what the question which most people would ask. So when I shuffle cards and I distribute them, is this distribution random or not? When I go and take a random sample from the population, is this random or not? Is it true that the probability of picking one person was out of 1,000 was 1 in 1,000? Is it true? So these questions are wrong questions. They represent a confusion between model and reality. So for example, there is a very neat example in physics that when you look at particles of light, photons, then what happens is that when you do one type of experiment, then you observe phenomena, you pass them through 2 slits and you put a screen at the back, then it seems like there is that they are particles because they behave like particles. Yani you can see, you can try to find out which of the two slits the particle went through, which is different from the what the waves are. That the waves are everywhere at once, so you can't. But if you look at the screen, you see what's a phenomena which is called cancellation, which occurs in waves. And when two waves collide and they are going to exactly the same opposite frequencies, then they cancel and there's nothing left. So on the screen, it seems like the particles are that the light is a wave, but when it's passing through the slits, it seems like it's a particle. It can go through one or the other, it can't do both. So the question arises, is light a particle or a wave? Now this question is wrong, in the sense that what we are saying is that when it comes to the screen, the model of light as a wave works well. When it comes to the diffraction grating, the model of light as a particle works well, and there is no contradiction because light is neither a particle nor a wave. Just like that, the question of whether when you flip a coin, is this a random variable? This question does not make sense, because the coin flip is a real world event, and a model is in our mind, and these two things are completely different, and one cannot be the other. So when you say all models are false, this is a level 1 understanding that models are different from reality. Another way to say it, and this is something somebody has said very nicely, is that there are things in the English language which are called metaphors. Metaphor is like saying Sarfaraz is a lion about some person. Now, this is a metaphor because obviously Sarfaraz is not a lion. So when we are saying is that that if somebody was to say, oh, Sarfaraz is a lion, where is his tail? Then that would be confusing the model with the reality. So when I say Sarfaraz is a lion, what I mean is that there are some characteristics of lions which are characteristics of Sarfaraz, not that they are the same. So when I say that the coin flip is a random variable, this is also a metaphor. I am saying that I have a model of random variables in my mind, and this model has some properties, and these properties are like the properties that the coin flip will have. Or at least I think so. This is where the models are useful or not. If the coin flip has the properties that my model also has, then I can say this model is useful. If, however, the coin is very biased, it always comes up heads, then I will say that this model is not useful. In neither case can I say that, oh, this model is true because it matches, and this model is false because it does not match. All models are false because all models are in the mind, and the reality is completely different, and the model can never be the same as reality. So actually, when you say all models are false, you are still displaying a level 1 understanding, in the sense that you think that some models might be true, but when you come to a level 2 understanding, you say that the question of model being false or true does not make sense. Models you cannot even put the two things can model it together. So we know in advance without having to discuss. So the only question is how and when models can be useful. So this is the question to study. And when this question is studied, then you understand that there is no point in studying models independently of applications, because it's just a mental study which has, until you establish that this model can be useful in some real world context, there is no point in studying the model separately. Unfortunately, the way that mathematics is taught, the way that econometrics is taught, people are taught only models, and then they are taught to believe that the models are exactly the same as reality. So this is a major source of confusion. So when we say, okay, let y be a random variable, y is consumption, now consumption is equal to alpha plus beta times gn plus epsilon, where this is. So you ask, is this true or is this false? It's just nonsense. So we have some series of data which have been generated by some, who knows, God knows only how. And now we say that I have a model of the consumption function, which is a mental model. Would this be useful in studying these data series? So this is a practical question. And when you say, okay, will it be useful? You have to ask, for what purpose? Why are you going to use this model? So it might be, if you study economics, that I will use this to predict the aggregate demand. And once I have the aggregate demand, I will use this to formulate monetary policy. Because if the aggregate demand is too high, then I want to follow a restrictive monetary policy. And if the aggregate demand is low, then I want to follow an expansionary monetary policy. Then I can say, okay, now here is my estimation method, and here is the policy. And suppose I use this estimation, I follow policy, does this have good effects on the economy or does it have bad effects? So in that context, I can say that, okay, this model of consumption function works well, because when I use it to make monetary policy, I make the right decisions most of the time. To ask independently and abstractly whether this is a good model or a bad model makes no sense, because the model has no match to reality. Alright, so this is something which is not very well understood. Now, you have studied the theory of one variable and its distribution. Now I want to study the theory of two variables and their distributions. And before I do that, I want to explain the context in which these models are used, because that helps to understand what is going on. And that is why, if you look at conventional texts, you will find only math, and you will find it difficult to understand what it is all about and how it can be applied. So let me, this is the original data on Pakistan from the World Development Indicators. Chala gaya. We get it back. All right. So this is all of the time series on Pakistan, which is based on World Bank data set. Now I'm going to just take two series, because I want to look at two random variables. And so here is one series. This series is called Broad Money in Current LCU. So this is broad money in current LCU. LCU is local currency units, which means Pak rupee in this particular case. And then there is GDP in current LCU. That's also GDP in current LCU. Now this is the number 7252. It's 7.25 million rupees, and then it became 6.96 rupees in 1961. There was a contraction in the money supply, and then there was growth, and so on. And similarly, we have GDP measured in rupees. So, so these are two data series. In some situations, it might be useful to think of them as random variables. What situations are those? Well, basically, I have an observation, I have a sequence of observations. Money went this way and GDP went that way. And now I want to know if there is some relationship between these two series. When you have things which happen only once, then you cannot discover any relationship between them, because it just happened. X happened and Y happened. Was there any relationship? This always refers to some hidden thing which is underneath the observation, which is not part of what is observable. So this is a serious problem. So models are also models about what might be the mechanism which generates this data. So that's why this model does not have match to anything which we can observe, because it is behind the data. It is something which produces the data. So now once we model this as a random variable, what this does is it says, suppose I say that, okay, suppose that the broad money is a random variable. Then if it is a random variable, then what we are saying is that the value of the money was 7.25 million, but it could have been 8 million, it could have been 6 million, because that's what the random variable is. So it's talking about what might have been. Now the what might have been will never be observed. So you can never say, is this model true or is this model false? But you can ask in some situations whether it is useful or not. It will take a while for us to see why this model can be useful, but there are some situations. But right now, suppose I want to think of this as a random variable, then one of the things about a sequence of random variables, basically random variable models are useful only if they are repeated, because all of the theory that relates to random variables, the law of large numbers, the central limit theorem, relates to collections of independent random variables. There is very little information of value we can get from just one random variable. So models which deal with one random variable are usually not very useful. Sometimes they can be, but not often. So what I want to do is to study this as a sequence of random variables. But if I say, okay, this is a random variable and this is a sequence, it's almost immediately true that this is not going to be a useful model. Why is it immediately obvious that this is not going to be a useful model? No. A random variable is independent and identically a sequence. I want to think of this as a sequence of IID random variables. But this doesn't satisfy basic conditions for IID random variables. Why? Independent का तो उतना मसला नहीं है, यानी I don't know. Independence को भी हम check कर सकते हैं. That's also possible. But the problem is more serious with identical distribution. These are numbers which basically just keep increasing. The increase means that it cannot be the same random variable which is observed over time. So One way to deal with this, which is often done, is that you put in a model. So for example, you suppose you take a linear trend. So you have a trend. Now you look at deviations around the trend. So if you look at deviations around the trend, they have a chance of being an IID random. They may not be, they may be, but this thing doesn't have a chance of being IID. Similarly, the GNP doesn't have a chance of being IID because both of these are increasing. So I want to look at random variables. I want to actually construct models of random variables. So what I did was to look at the rate of growth. Now the rate of growth is often a random variable because now it's 6%, 5%, etc. So in this cell, I look at F2 over E2, which is the 1961 broad money divided by the 1960 broad money, and that comes out to be 96%. Then in 1962 it was 109%. And so on. So now you can see that these numbers are all similar in some sense. So there is a chance that we can use a random variable, IID random sequence here. I did the same thing for the GDP. I converted it to rates of growth, and then I got 109% and 4%. So now this has some chance. I want to look at these two random variables together. But just to simplify, because it's much easier to understand discrete random variables than it is to understand continuous random variables, so I wanted to do what is called discretization. Basically, what I did was, I said that, okay, take this growth rate, 96%, divided by 0.05, and then round it off to the nearest integer. So if the growth rate is 100%, which means if this number is 100%, which means growth rate is 0, then you will get 20. If it is 105, the next one is 109. So from 0 to 5% growth, you get 20. From 5 to 10%, you get you get from 0 to 5, you get 1. From minus 5 to 0, you get 0 by the process of rounding. So from 0 to 5, you get 1. From 5 to 10, you get 2. From 10 to 15, you get 3. It's just a way of discretization. Just converting a sequence, a set of values to integers and approximating so that in one bracket from 0 to 5% you get just one number. So this means this reduces it to a integer valued random variable, and this goes from 20 to some 27, I think. That's the largest value. Anyway. Then, in order to get rid of these 20s, I just subtracted 20. And so, the money growth random variable is 0 in 1961, because actually the money didn't grow. It actually went minus 4%. Then it is 2 in 1962, which means it grew by between 5 to 10%. Then it is 4, this one goes from 17%, so this is 15% to 20%. 5 means 20% to 25%, and so on. So these are just numbers which represent the growth rates. And similarly, I did exactly the same thing for the GDP growth. So 2 means near 10% growth, 1 means around 5% growth, and so on. So these are the numbers. Then what I did was I converted this data to, I copied this data over here, and I want to look at what happens. So this is money growth, and this is GDP growth. So in the first year, 1960, there was 0% money growth and 10% GDP growth. In the 62 there was अच्छा ये मैंने sort कर दिया है, so it's no longer year 1 and year 2. So then to construct my multivariate random variable, I recorded the possibilities for money here. In this column I have yearly growth, yani GDP growth, and in the other column I have money growth. And then I counted. So 0, 2 में 1 है ये, which means that there was one instance in all of these years in which the money growth was 0 and the GDP growth was 10%. This is blank, which means this never happened. There was 1 year in which money growth was 5% and GDP growth was 10%, and so on. These 4s, these are the biggest numbers, and 6 here. So the largest number of cases were the ones where money growth was 20% and GDP growth was 15%. That happened 6 times apparently. Remember that this is nominal. So 15% growth is not real 15% growth. This means, so basically one of the things I want to check is money growth proportional to GNP growth. So if money growth is proportional to GNP growth, then we would see big numbers in the diagonal and small numbers off the diagonal, and more or less this seems to reflect this. So now how do we use this model? Well, so far I don't have a model. So far I just have observations. Now I want to consider the situation where all of these 7 numbers are chosen at random. Yani in any year. Alright, let me make it easier. Suppose that what happens is that the monetary authorities randomly choose one of these 7 growth rates. They either have 0% growth in money, or they choose 5%, or they choose 10%, or they choose 15%, 20, 25, 30, 35. So the monetary, they go to the central bank, say, okay, this is how much money we are going to print this year. Then as a result, GNP growth occurs. Well, actually, it may occur because of the money, or it may occur from some other reason. We don't really know. So now, let me copy this over some other place to see what we want to do. Alright, so now I have 7 categories of one random variable and 7 categories of other random variable. Now what I am going to do is to ask first, now I'm going to study an abstract model for a little while. Then we will see if I can take one of these abstract models and match it to the data. But now I am switching to a different model. Now we are in mental model realm. Now I am thinking abstractly. There is one random variable which takes 7 possible values. There is another random variable which takes another 7 random variables, possible values. So I can name these variables. Let's say that the top variable is called M, and so and this variable is called y, and the variable y takes these 7 values, and the variable m takes those 7 values. Now, both of these occur at random. Let us suppose that they are independent to make life easy. Now, and let us suppose that they are all equally likely to happen. That makes life easy because there are 7 times 7, 49 cases. Oh, sorry, I have this 0 which makes things different. Let me keep the 0 and eliminate this 7 so that we have 2 different variables. The first one varies from 0 to 6 and the other one varies from 1 to 7, so that we don't get confused between which is which. So the one of the variables is m and the other value is y. Now still there are 7 and 7 possibilities, so the total of 49 possibilities. So all of these cells are equally likely with possibility 1 over 49. So let's see. Let's see, how can I generate this? Alright, equals rand between now what I know is that in 49 trials I will see 1 observation in this cell. So let us suppose that there are 490 trials that we make. So there are 490 different observations that we make on this pair of random variables. So then I expect to see about 10 values in this, but it will be random. We don't know how many times. It may be bigger than 10, maybe less than 10. What I'm going to do is put in rand between 5 and 15, just to, so this chooses any number between 5 and 15, but on the average it will be 10. So this is a guess, so this comes out 12. Now what I am going to do is to replicate this, and then what I am going to do is replicate this in this direction. Alright, so now the problem with rand between is that it will keep changing and I want to keep these numbers fixed. So I am going to copy this, or I can just cut it and then I paste values. So it doesn't allow me to, that doesn't help. Okay, so I'm going to copy this and I'm going to paste this here, just the values. Okay, and then I can just delete this because it's just going to interfere. Alright, so now I have some numbers of observations which occurred for these 2 pairs. This is not a random variable, this is just some numbers that I have seen. Now what I want to do is to construct a random variable which has a chance of being a model for this these observations. So that can be done by assigning probabilities to each of these cells. Right. So, right, okay, let me just do that. Copy this once again. All right. So the model that I would like to think of initially is to say that, okay, each of these cells has probability 1 over 49. So this is the probability of this cell, and that's the probability of all of the cells. So this is my model. The model gives the probabilities of each of the cells. Now I want to ask the question that, actually, because I constructed it this way, so I know that this model is exactly the right model which actually generated those numbers. But in typical applications, like the previous one, I will have some numbers and I will have some model, and I would like to see if this model corresponds to if this model is a sensible model for those numbers. If there is a match between what the model predicts and what actually happens. Yes. So, how do we do that? 10,490. Okay. So, in order to do that, what I need to do is to look at what are the numbers that are observed when this model is used to generate numbers. So now I am faced with the question that, suppose I have a probability model which says that each of these 49 cells has probability 1 over 49, and suppose that I want to generate 490 observations of these two variables. This is the task. So I want to know how this model works. Now, this model is a mental object, but the calculations are too difficult. We can't hold it in our mind, so we hold it in Excel. But still, it is not a reality. It is a mental construct. So, how you generate numbers from this? There are a number of different ways to do that. This is actually what is called a multinomial distribution, which has its own theory, but that's not useful for us for the purpose that I am studying. So what I am going to do is to look at what is called the marginal distribution. So the marginal distribution of y, this is my column variable is y. We know the concept of distributions for single variables. Now what I am trying to do is to explain the concept of distribution for two variables. So the marginal distribution of y is the probability that y equals 1. Right? That's all. So I want to write here probability y equals 1. Now, because I don't have any direct understanding of y equals 1, because I don't have, because we have two variables. So how would you get the probability of y equals 1 from this table?
Summing those coefficients.
Exactly. You sum all of the possibilities. There are 7 different possibilities, either y equals 1 and x equals 0, or y equals 1 and x equals 1. So there are these 7 events, and all of these 7 events are mutually exclusive events. This is very important. So if one of them occurs, the other one cannot occur. That means that you can add the probabilities. So we can just get the probability of y equals 1 by adding all of these. And that's 0.142857. What is that? That is 1/7, of course, right? And similarly, so probability of y equals 1 is 1/7, and probability of y equals 2 is 1/7, and so on. And similarly, if we do this, so the marginal probability of x or m is also 1/7 for each of the possibilities. क्या हुआ? Because we put everything as 1/49th here. Now, I want to generate random variables, 410 of them. So, the way to do that is to first generate one of these variables and then generate the other one. That's one way to do it. There is a direct way, which is from the joint distribution, which is how I did it the first time. All right, so I can do it, but I'm thinking,
Sir, ये joint distribution तो marginal फिर jointly marginal जो हमारे को बोलते हैं वो joint distribution के लिए single लगी है तो हम लोग निकाल सकते हैं.
क्या हुआ?
अभी ये हमारे टेबल बना हुआ है joint distribution आपने कहा जो हमारी marginal probability निकलेगी तो वो x यानी row wise और column wise जो दो हमारे event होंगे उन दोनों का होगा single से एक कितनी होगी जैसा आपने लिखा y is equal to 1 probability of y is equal to 1.
Yes.
वो सिर्फ 1 की तो नहीं होगी, this will be 1 and 0 or 1 or 1 इस तरह होगा.
That is what the marginal probability is. It's probability y equals 1.
Y की value same है ना इससे?
Y is 1 across all the other possibilities. So y equals 1 and there are 6 possibilities for the other variable. All of those are accounted for, so this is just y equals 1. Now, what I'm going to do, I'm going to make this a little bit more complicated, because when all the variables are same, you won't be able to understand what's going on. So what I'm going to do is to make the probabilities different so that things are easier. So what I'm going to do is to say that I'm going to take these outcomes, which are not probabilities, I'm going to convert these into probabilities. So first I need to do is sum everything. Okay, so let's look at what is the sum. Equals sum. I wonder if I can do it like this. Will it take it? I hope so. So there are 474 total random variables, right? So I'm going to convert this to, I'll do it like this. इसको मैं change कर देता हूँ. Equals this divided by 474. Alright, so now I have changed the probabilities so that they are all different. The first marginal probability of y equals 1 is 0.149, and this is 0.13, 122, and so on. And similarly, these probabilities are different. Now, what I want to do is to generate random variables according to these probabilities. So, one way to do this is to first generate a random variable y according to these probabilities. Alright, so I will, there are many ways to do this. I'm going to show you one way. I'm trying to find a way which will be the easiest for you to understand, and let us hope this works. So first I'm going to take the cumulative distribution . No, not like that. Let me change this to this, yeah. Alright, so this is the cumulative distribution, right? So probability that y equals 1 is 0.149, probability that y is less than or equal to 2 is 0.28, probability that y less than, I've just added the variables. So now, I have 490 variables, yes. And I generate 490. Ouch. Okay, let me do it like this. So, what is the probability that y equals 1? Alright, this will make. The probability that y equals 1 is 149, etc. 0.149, 14.9%, right? So now, in 474 trials, how many times will we see y equals 1? Huh? नहीं, ठीक है. That is the expected value. We will see 14.9% of 474. But I want to generate a random variable which has 14% chance. What I want to do is to take 474 trials. On each trial, there will be a 14.9% of this variable coming out 1 and a remaining chance of not being 1. So this will be a binomial random variable, right? So this will be equal to, I want to generate a random variable which is, okay, so let me do that. So this will be binomial. I'm just writing down words here. Binomial with 474 trials and success probability 0.149. Actually, I can make it 0.149789. That's the success probability. Oh, I see. Yeah, okay, so that's binomial and P. Alright, that's all. That's all. Yani, I want to generate a variable like this. So I can do that by going into my data and data analysis, random number generation, number of variables 1, number of random 1. I go into a binomial and the p value is 0.149789. Number of trials is 474 and output will be exactly here. That's it. Okay. So there are 63 trials which came out like this. Now here I will generate a binomial 474 with probability 0.135. नहीं, ये वो मैं एक और तरीके से कर रहा था, उसको मैंने छोड़ दिया. So I do this one more time and I generate this number and I will get some other number. क्या हुआ? क्या हुआ? कमांड कर लेते हैं. कैसे कमांड करते हैं? बाइनोम डिस्ट. दैट वोंट वर्क ना. अच्छा, तुम लोग को बाइनोम डिस्ट इनवर्स है? I don't think so. Norm inverse है, binomial disk inverse नहीं है. Generating binomials, there are other ways to do it. मगर वो they require some. Okay, let me just do it one more time, just to show you what's going on. Okay, now 149 के बजाय हमें इसमें 0.135. That's good enough. इसको बदल देना चाहिए to be here. Okay, so this came out 60. Now let me just randomly fill this up as 65, 70. क्या हुआ? राइट, तो 6 नंबर तो हम ऐसे जनरेट कर लेंगे, मगर जो लास्ट है वो हम ऐसे नहीं जनरेट कर सकते, क्योंकि द सम ऑफ ऑल ऑफ देम हैव टू बी 474. So this will be 474 minus all of these above. Now, once I have this, then we get to the second part, which is what the last thing I want to do, is that for each of these trials, I want to generate the other variable. And so I will say, there are 63 cases in which y equals 1. Now, what is the value of x? So, in this situation, I would look at the conditional distribution of x given y. So, I want to just show this, and this will be the last thing. What is the conditional distribution of x? Let me just write this in words. Conditional distribution of x, or that was m actually, given y equals 1. अच्छा, तो that will have probabilities. देखो यहाँ पे जो marginal probability है, यानी we are just looking at this first line only. बाकी सारे numbers irrelevant. So now the probability of 0 will be equal to this divided by 0.149. I'll put this down like 0.149,789. Enter. So the 0 probability is 15%, and now I can carry this around up to here, even the last one. So probability of m equals 0 is 15%, probability m equals 1 is 14%, probability m equals 2 is 11%, 3 is 18%, and so on. So this is the conditional distribution of m given y equals 1. So now I can generate these for each value of y, and I can do this 63 times. This will actually also be a binomial variable. Actually not a binomial, this will be a multinomial variable. I will have 63 trials of a multinomial variable in which there are 7 different categories, each which has known probability. So I can generate this from a multinomial distribution. Now I have another multinomial distribution, and that is for the case of these are the conditional probabilities of m given y equals 2, and then so on. So we have 7 different conditional distributions. So basically this is how the bivariate distribution works. These numbers over here, these are called the joint distribution of y and m. In the joint distribution, you give the value of both of the variables, and then you ask what is the probability. In the marginal distribution, ask what is the value of one of these variables separately on its own by itself. And in the conditional distribution, ask what's the value of m given the value of the other one. So the joint distribution can be decomposed into a marginal of y and the conditional of m given y. It can also be decomposed in the other way as the marginal of y and the conditional of m given y. So there are these 5 distributions that we have when we work with bivariate variables. There is the joint distribution, the marginal of x, the marginal of y, the conditional of x given y, and the conditional of y given x. These are the basic concepts that you need to work with multivariate. Now the distribution here, for one variable y, the distribution is just the marginal distribution. For the variable y, it's just the marginal distribution of y, marginal distribution of m. The conditional distribution is also univariate distribution, but there are many of them. For each value of y, you have a conditional distribution of m given y. So there are 7 different ones and an infinity of them when you have continuous variables. Similarly, you have the other conditional distribution. Then you have the joint distribution, which is directly both variables taken together. So these are the 5 distributions that we need to learn what they are, how you make calculations. That's how multivariate variable theory works.
सर देन हम यहाँ से भी निकाल सकते हैं कि अगर y गिवन है हमारे पास, देन हम x की कितनी वैल्यूज आ सकती है, जैसे हमने वहाँ से 66